A novel recursive method for integrity verification of measured transformer currents is proposed, tailored for modular development of hardware-in-the-loop digital twins, HIL DTs. This approach leverages the Adaptive Extended Kalman Filter to estimate parameters of transformer currents, which may exhibit non-sinusoidal behavior during transients, such as transformer energization. The Adaptive Extended Kalman Filter's ability to accommodate nonlinear systems and non-Gaussian noise makes it an ideal choice for this application. By recursively updating the state and error covariance matrices, the filter provides a robust and adaptive estimation of the transformer current parameters. The performance of the proposed method is evaluated using EMTP-RV for simulating transformers and Matlab for executing the proposed method. Simulation results demonstrate the method's capability to accurately estimate and closely track the current measurements, even in the presence of noise and model uncertainties. This research contributes significantly to the development of HIL DTs for power transformers, addressing the need for accurate and continuous measurements with a high sampling rate. The proposed method's ability to handle non-sinusoidal currents and provide real-time estimation makes it a valuable tool for ensuring the reliability and efficiency of power transformers in various applications. A novel method for modular measurement integrity verification is proposed for hardware-in-the-loop digital twins replicating single-phase and core-type 3-phase transformers. This approach employs an adaptive extended Kalman filter to recursively estimate transformer current parameters during both steady-state and transient situations. The filter evaluates the validity of the estimations and, if valid, reconstructs the measurements with suitable sampling rates for numerical differential equation solvers. The proposed method's modular architecture enables users to gradually extend the digital twin based on their priorities. The Adaptive Extended Kalman Filter estimates transformer current parameters even when the transformer is heavily saturated, leveraging its recursive mathematical formulation to achieve computational effectiveness. This makes it suitable for implementation in industrial computers. Additionally, the filter adaptively modifies itself with respect to measurement noises, increasing its accuracy and trackability. The method consists of 4 modules: a current parameter estimator, an estimation validity evaluator, a noise parameter estimator, and an interpolator. Each module is loaded in each processing unit, allowing users to add or remove modules based on their needs. The current parameter estimator removes noises and estimates the parameters of the measured current. The estimation validity evaluator assesses the validity of the estimations, and if valid, the noise parameter estimator finds the noise parameters. Finally, the interpolator module reconstructs the measurement at a sufficiently high sampling rate. This approach offers several advantages, including its ability to estimate parameters of measured currents even when the transformer is heavily saturated, its computational effectiveness, and its adaptability to measurement noises. In the processing of measured samples, the parameter estimator module is the initial stage. The transformer current consists of 2 components: the magnetization current and the sinusoidal component. The magnetization current is proportional to the total flux linkage and can be approximated using a 2-term polynomial. The sinusoidal component is characterized by a peak value, power system angular frequency, and initial phase. Noise contamination necessitates the application of an estimation method to remove the noise. A comparison of various methods, including Fourier-based methods, Savitsky-Golay filter, Prony method, matrix pencil method, short-time matrix pencil method, discrete wavelet transform, and Kalman filter, reveals the Adaptive Extended Kalman Filter, AEKF, as the optimal choice due to its high trackability and accuracy in measuring power system transients. The observer equation is formulated using the transformer current, which is based on the core's total flux linkage. A simplified and discrete time form of the flux linkage is employed, considering the residual flux linkage and decay time constant. The magnetization current is approximated using 2 polynomials with distinct parameters for single-phase and core-type transformers. The states and coefficients are defined, including the sinusoidal flux linkages representing a combination of limb and yoke fluxes. 4 states and 4 coefficients are required for representing the magnetization current. The AEKF's high trackability and accuracy make it an effective tool for estimating the transformer current, enabling accurate monitoring and analysis of power system transients. The proposed method for real-time estimation of the magnetic field in single and three-phase transformers employs an adaptive extended Kalman filter, AEKF. This approach minimizes the need for prior knowledge by considering the transformer current as a combination of a decaying term and a sinusoidal component, each with its own states and coefficients. A state space representation of current measurements is developed, and the AEKF is used to estimate these states and coefficients. A buffering time is required before sending the estimations to the next steps. An estimation validity evaluator module assesses the estimated samples independently of future samples using hypothesis testing. The method recursively updates the measurement noise variance and estimates the residuals, mean, and standard deviation for normalizing the residuals. This novel approach enhances the accuracy and efficiency of magnetic field estimation in transformers, providing a significant advancement in the field. A novel real-time, adaptive, and hybrid state estimator is developed for single and three-phase transformers, combining the strengths of model-based and measurement-based methods to provide accurate and robust transformer state estimation. This estimator employs an adaptive extended Kalman filter, AEKF, to estimate transformer states, which are then validated using a hypothesis testing approach. If the estimation is deemed invalid, it indicates an abrupt change in the transformer's operation, requiring further investigation. The AEKF module estimates the measurement noise variance and utilizes a recursive sum of the last m residuals to normalize the kth residual. A threshold t is determined based on the probability of false alarms, and if the normalized residual is smaller than t, the estimation is considered valid. Otherwise, it is invalid, indicating a potential issue with the transformer. The noise parameter estimator module updates the measurement noise variance using either equation 21 or the proposed equation 22 for improved computational performance. The interpolator module reconstructs samples at a high sampling rate suitable for the solver, using equations 23 to 25. The proposed method was tested on a single-phase transformer and a three-limb, core-type, three-phase transformer using EMTP-RV. Simulation results were downsampled and Gaussian noise was added to simulate real-world conditions. The results show that the proposed method is effective in estimating transformer states under these conditions, with a probability of false alarms set at 0.01 and a corresponding threshold of 2.575. The following summary presents the results of the no-load test and energization test using the proposed method for estimating transformer currents. A single-phase transformer was used in the experiments, with parameters including resistances, inductances, and other relevant values listed in Table I. The no-load test results are presented in Fig. 4, where the measured and estimated no-load currents on the low voltage, LV, side are compared. The estimated current is found using the function h, aakk, xxkk, and the results show a good match despite considerable noise. The residuals between the measured and estimated values are calculated using equation 16 and shown in Fig. 4b, with the largest residual highlighted. The normalized residuals are presented in Fig. 4c, where the largest residual exceeds the threshold of 2.575. The estimated sinusoidal component of the transformer current, IISS, is shown in Fig. 4d, which matches the measured value closely. The estimated magnetization current, IIMM, is presented in Fig. 4e, also showing a good match with the measured value. The errors in the estimation of sinusoidal and magnetization components are shown in Figs. 4f and 4g, respectively, with acceptable errors considering the complexity of the model and approximations. The energization test results are presented in Fig. 5, where the measured and estimated inrush currents on the LV side are compared. The LV side is energized at TT equals 0.1 s, while the high voltage, HV, side remains open. The initial flux of the core is 0. The estimated inrush current becomes valid quickly despite deep saturation. The normalized residuals related to the estimation of the inrush current are shown in Fig. 5b. with small peaks caused by decreasing mismatches between the estimated and measured sinusoidal components. The estimated magnetization component matches the measured one shortly after switching, as shown in Fig. 5d. The inrush test results for different switching angles and transformer loadings are presented, with the mean squared errors, MSEs, of the estimated currents calculated and shown in Table 2. The MSEs are smaller when the switching angle is close to 45 degrees. The performance of the proposed method in underload switching of the transformer is demonstrated in Fig. 6, where the LV and HV sides of the transformer are switched to sources with different voltages and phases. The measured and estimated LV and HV currents are shown in Figs. 6a and b, respectively, with the transient parts decaying fast as the transformer is under load. The normalized residuals are presented in Figs. 6c and d, highlighting the abrupt changes in both LV and HV currents due to the LV side switching. The estimation errors in underload switching for different transformer loadings are evaluated, as presented in Table 3. The results show that lower MSEs occur when a higher portion of the power is active. Figs. 6e and f show the estimated sinusoidal components, and Figs. 6g and h show the estimated magnetization components. The sinusoidal current is correctly estimated in a shorter time when it is comparable to or larger than the magnetization current. A hybrid model of a core type, 3-limb, 15 kVA, 60 Hz, 208 Y, 240 delta distribution transformer is presented, made in EMTP-RV with the given parameters in Table IV. The transformer is energized with its nominal voltage at 0.016 S from the LV side, while its HV side remains open. The measured and estimated currents of phases A, B, and C are presented in Figs. 7a, b, and c, respectively, with the normalized residuals shown in Figs. 7d, e, and f. Despite the core becoming highly saturated, the proposed method is able to estimate the currents accurately. The results of the energization test demonstrate the effectiveness of the proposed measurement integrity verification method for transformer currents. Figure 7 displays the measured and estimated currents of phases A, B, and C, alongside their normalized residuals, estimated sinusoidal components, and magnetization components. Despite some negligible mismatches due to the complex behavior of transformer cores, the method accurately estimates the currents. The normalized residuals in figures 7, D, E, and F illustrate the combination of errors in the estimated sinusoidal and magnetization components, primarily consisting of noise, indicating successful estimation of both components. The effect of measurement reconstruction on digital twins, DTs, is also explored. Figure 8 illustrates the measured no-load current of phase A with and without additive noises, as well as the reconstructed measurement with a high sampling rate. Table V presents the calculated areas between the measurements and the time axis, along with the relative errors with respect to the reference case. The results show that the proposed method significantly improves the accuracy of the calculated areas. The proposed recursive method ensures measurement integrity verification in transformer currents, particularly in the context of hardware in the loop, HIL DTs. The method's modular structure enables its gradual extension to DTs, and the Adaptive Extended Kalman Filter, AEKF, is employed to estimate the parameters of measured currents. A hypothesis test is used to evaluate the estimations, and the valid ones are utilized in the reconstruction of measurements. A novel digital twin framework is proposed for power transformers, enabling the estimation of current measurement parameters and tracking of changes in transformer currents, even under intense core saturation. This innovative approach is evaluated through a combination of EMTP-RV simulations and Matlab-based execution of the proposed method. To validate the framework's efficacy, several scenarios are defined, and the results demonstrate satisfactory estimation of current measurement parameters and accurate tracking of transformer currents. The digital twin's ability to operate under intense core saturation is a significant advancement, as it allows for more accurate monitoring and prediction of transformer performance. The proposed method's technical underpinnings are rooted in a thorough understanding of magnetization currents, which are critical in power transformer operation. Hypothesis testing is also employed to ensure the validity of the digital twins estimates. The development of digital twins for power transformers is a crucial step towards realizing real-time monitoring and predictive maintenance capabilities. This research contributes to the advancement of this field, providing a foundation for future work in the development of more sophisticated digital twin frameworks. The paper provides a comprehensive review of the current state-of-the-art in power system engineering, focusing on transformer inrush currents and their impact on power system operations. It begins by discussing the fundamentals of transformer inrush currents, including their definition, causes, and effects on power system operations. The authors highlight the importance of understanding and mitigating inrush currents to ensure the reliability and efficiency of power transformers. The paper then delves into various methods for mitigating inrush currents, including the use of controlled switching techniques, shunt active power filters, and harmonic and interharmonic phasor estimation methods. Detailed descriptions of these methods are provided, along with their advantages and limitations. In addition, the paper explores the role of digital twins in enhancing the efficiency and reliability of power transformers. Digital twins are virtual replicas of physical assets that can be used to simulate real-world conditions and predict potential issues before they occur. The authors discuss how digital twins can be used to optimize transformer performance, detect potential faults, and improve maintenance strategies. The paper also covers recent advances in power system state estimation, including the use of sparse Kalman filtering and matrix pencil methods for estimating harmonic and interharmonic phasors. These techniques are essential for accurately measuring power system quantities under sinusoidal, non-sinusoidal, balanced, or unbalanced conditions. Furthermore, the authors discuss the importance of powerline carrier line traps and their requirements according to IEEE standards. They also touch upon the reduction of three-phase transformer inrush currents using controlled switching strategies and the use of three-state Kalman filters for directional protection of power transformers. Finally, the paper concludes by highlighting the need for continued research and development in the field of power system engineering, particularly in the areas of inrush current mitigation and digital twin technology. It emphasizes the importance of collaboration between industry and academia to address the challenges facing the power sector and ensure a reliable and efficient supply of electricity.